members of the conference who gave me an opportunity to present the part of my PhD thesis work, which is done at Udaipur Solar Observatory under the supervision of Namita Srivastava. Here I will discuss about the interaction of CMEs and their evolution and their consequences, heliospheric and geomagnetic both. First outline, I will give the brief introduction about the availability of CME observation in SOHO and stereo era. Then I will highlight two open questions regarding interaction of CME and our approach to answer those questions by studying the two cases of interacting CMEs of 2011 February and 2012 November. Then results and conclusions. We all know that coronal mass ejections are huge magnetized plasma expulsions from the sun into heliosphere, and they are drivers of many space weather events like geomagnetic storms and substorms. In SOHO era, majority of studies were carried out were based on the 2-point measurements, one near the sun by the coronagraph LASCO and other near the earth by the in situ measurements. Such studies couldn't explore the evolution of CMEs in the distance gap outside the 30 solar radii to the earth. So we have to depend on the various drag-based model and MHD models. However, it has been shown earlier that such studies based on 2-point measurements were always erroneous to predict the arrival time of CME. This is because evolution of CME is poorly understood. We don't have the quantification of various forces acting on the CME, and moreover the CME-CME interaction or the collision. Both can change the dynamics of CME significantly. After the launch of stereo in 2007, we can have a continuous coverage of CME from the sun to earth or even the beyond. And moreover, we have the multiple viewpoints of stereo A and stereo B. Stereo A is moving in the earth's orbit ahead and stereo B is in the behind. So the separation between both is increasing by 45 dB per year. So we have an opportunity to do 3D reconstruction of CME. CME interactions are expected around solar maximum when the launch rate of CMEs are more. The first postulates are, I can say, conjecture was given by Intelligator and Burlaga very early using the in situ observations of CME that CME might be interact. First evidence of this interaction was given by Gopal Swami et al. 2001 using the white light image of LASCO and radio enhancement. In this image we can see that both CME high time track gets merged here, and at the same time they found the radio enhancement. There are few studies which suggest that interacting CME can lead to strong geomagnetic storms. After the launch of stereo, there are only few studies because sun was in deep minimum, so there were not very frequent CME launch, but there are only few which has been studied. However, we have many questions which have not been understood or has not been focused in earlier studies. These are how do the dynamics of CME change after interaction, or what is the regime of interaction. If we know the regime of interaction, we can get the improved prediction of arrival time. What are the consequences of interaction of CME shock structure? How the shock affects the plasma parameters of the preceding CME? Do these interacted CME structures have different geomagnetic response to the earth than the isolated CME? And what are the favorable conditions of CME cannibalism? So to answer these questions, first I selected the case of interacting CME of 2011 February 13 to 15. So there are 3 CME. We termed as CME1, CME2, CME3 launched on 13th, 14th and 15th February. Earlier, first we did the 3D reconstruction of these CMEs in core 2 field of view using the GCS model, graduated cylindrical cell model. We fit the flux slope of all these 3 CME, and we plotted here in this figure we plot the latitude, longitude, acceleration and velocity of these 3 CME. Earlier estimates in this core 2 field of view suggest that this CME might interact in the heliosphere. In this movie, then we followed this CME in the HI field of view, and we can see that this CME seems to interact in the heliospheric imager, HI1 and HI2. This covers the 15 solar radii to 90, and this from 12 to 380 solar radii. So we have a continuous coverage. But the problem is when the CME comes in HI field of view, it becomes very diffuse, and we cannot identify an individual feature to estimate its kinematics. So we constructed the J map using the heliospheric imager 1 and imager 2 data for the stereo A and stereo B both. And here we can see that we have the 3 tracks. This technique is actually developed by earlier Silly et al. And routinely it is used to track the CME. Here we can see that 3 tracks, red, blue and green, corresponding to 3 CME, CME1, CME2 and CME3. We track and we derive the time elongation profile from this J map. We also made this J map for the stereo B. So we had the time elongation variation from the both viewpoints of stereo A and B. And then we applied the another reconstruction techniques, stereoscopic self-similar expansion, in which we assume that CME is like a sphere and its one end is always attached to the sun. Using such reconstruction technique, we could derive the distance, direction and speed of this CME. Here we can see that CME2, which is slower, has been caught by the CME3, which is faster. And at the same time we see the exchange in speed. The CME3 gets decelerated while the preceding CME2 after February 14 gets accelerated. So such scenario looks like a collision phase, and we define this collision interval with these two vertical dashed lines as a considering that when the two correct features of the different CME come in close contact with each other until they get separated or they get the approximately equal speed. We wanted to study the momentum exchange and collision dynamics, so we calculated the mass of this CME. Historically, the mass of CME is calculated using the plane of sky approximation. However, to understand the true dynamics, we need to understand the true mass or the mass. We need to resolve the projection effect. So we estimated we use this method of collision overlay. Thus, our approach is slightly different. We estimated the MA and MB from the both stereoscopic viewpoints, and then we can solve some equations and we derive the true mass. Those are given here. Using this mass and the pre-interaction velocity and post-interaction velocity from this estimates, we calculated the coefficient of restitution. We followed this approach to calculate the coefficient of restitution, and we find that our coefficient of restitution for this collision is 0.90, which is close to elastic collision. Although there may be uncertainty in the mass estimates, because still while we resolve the projection effect, we assume that the CMEs are in one plane, so we don't have the information about the lateral extent of the CME, lateral extension of the CME. So that uncertainty is like 15%. It has been calculated earlier. So we took larger uncertainty, like 50% of uncertainty in the mass estimates and plus minus 100 kilometer uncertainty in the speed. Despite this, taking this uncertainty, we find that our coefficient of restitution is 0.7, 0.8. So taking these uncertainties, our result remains same. So we try to analyze the in situ observation of these CME near the Earth taken by wind spacecraft, and we find that these three CME could be identified as a region R1, R2, and R3, and these all are distinct. What we notice here that we have plotted the CMEs index at the bottom panel, which is the like a high resolution DST index, which measures the perturbations in the Earth's magnetosphere around the equator. And then we have plotted the magnetic field, these vectors like phi, longitude, theta, latitude, and then velocity, temperature, proton density, Vg component, and total magnitude of B. We notice that CME3 and CME2, which is preceding the CME3, have been compressed and have been heated. We can see here, especially CME2. And at the region of R1 and R2, we have sudden decrease in magnetic field, at the same time increase in the temperature and velocity. Such a distinct structure between R1 and R2 looks like a magnetic hole structure and seems to have the signature of magnetic reconnection. So we notice that interacting structures can lead to very strong star-sudden commencement, as we can see here that CMH index go up to the 57 nanostar. So we selected another case, interacting CMEs of 2012 November, and here we again, when we estimate the initial estimation go to field, we find that CME2 of November 10 have the speed higher than the CME1 of November 9. Again we have both Earth directed, we again estimated its steady direction, and we found that this again might interact en route from the Sun to Earth. So here we saw this core 2 HI1 and HI2 images of and from both viewpoints of stereo, and we noticed that somewhere in a HI field of view this CME gets interacted. We again made the J map for this CME. Here, contrary to earlier case of February 11, here we noticed that leading edge of CME1, 9th November, don't interact at all. It goes very fast, while the trailing edge, which has very high dense structure at the trailing edge, interacts with the leading edge of following CME of November 10. So we try to understand how the nature of collision differs in this case. We carried out the same plot that we determine the height time, and we again find that collision-like scenario. We estimated the pre-interaction speed and post-interaction speed, and again estimated the collision coefficient of restitution. And here we find that in this case coefficient of restitution is 0.1 almost, although we have taken huge uncertainty in mass and speed. So we wanted to see why this CME have a different coefficient of restitution exactly close to perfectly inelastic. So we again analyze the in situ observation of these CMEs. Here we notice that here we could see the shock which has been driven by the following CME2, and we could see the separate structure CME1 and CME2 separated by the interaction region. In this interaction region, what we see that there is a two dips, and this at the two dips in magnetic field. At the same time, we have the two jumps in temperature. So at the same time, we had the very sudden change in the latitude and longitude of magnetic field vector. So here we think that this CME had long collision phase and had interacted for longer time, so it produces the interaction region. And we can see that temperature has been increased. So again, this it looks like a interaction signature. So one inference what we get from here that once CME get interact or come in close contact, their flux rho might get some reconnection. And we wanted to see how this interacted structures have different geomagnetic response. We plotted the interplanetary electric field and PC indices, which measures the electric field in the polar ionosphere. And this we again plotted the CMEs index, which is the high resolution DST index, measures the perturbation at the Earth's surface around the equator. And we also plotted the air index, which measures the substorm activity night side of the magnetosphere. What we notice here that as interaction region arrives, we have the sudden change in all the geomagnetic indices. And we inferred that interaction region has the plasma parameters and magnetic field parameters, which have enhanced responsible for this major geomagnetic activity. So if we compare both results, we find that CME2 and CME3 of February 11, 2011 gets interacted very close to 25 solar radii. However, CME1 and CME2 of November 9th and 10th at 35 solar radii. If we use the estimates of speed in CO2 field of view and assume that these are constant, then this interaction sites or the site of interaction comes at to 130 solar radii, which is very far from the sun. It means that once CME leaves the CO2 field of view, even before collision, it gets very strong deceleration. And we explain this that earlier CME even don't have the contact with the CME2, but there are some magnetic barrier for CME2. So CME2 look as a CME1 as a magnetic barrier, so before get interaction or merging, it slows very fast. And we found the momentum, significant momentum exchange in both cases. Total kinetic energy has been reduced in both cases. However, in this February case, nature of collision coefficient of restitution is close to elastic, and in this November case, it is close to perfectly inelastic. One strong difference what we noticed that interacted CME of February 11 gives very strong storm sudden commencement, which is the very positive excursion on the Earth's surface of magnetic field, but small minor geomagnetic storms, which measures the ring current intensity. But the CME of November 12 has very strong major storms, and it means that at this time ring current intensity has been enhanced very strongly. So to conclude, I have made the points that a CME cannot be treated as a completely isolated magnetized plasma blobs for understanding their evolution and propagation in the heliosphere. Evidence of CME collision is revealed in both in situ observations because we have the signatures of magnetic reconnection and magnetic holes. Nature of CME interaction may vary from elastic to inelastic, and we want to further explore what are the plasma parameters of CME which decides this nature of collision. We have estimated the arrival time of these CME using various approaches. Like first we have taken the 3D speed in CO2 field of view, pre-interaction speed, and then we have used the post-interaction speed. And we have found that if we use post-interaction speed, there we get the improved prediction of arrival time of CME. So post-interaction kinematics must be taken into account for any space weather prediction. Collision occurs much closer to the sun than expected based on the CO2 observations. So we conclude that tracking of different features of CMEs in a child field of view and their association with in situ observation is necessary for understanding their evolution. Finally, we conclude that the heliospheric and geomagnetic consequences of colliding or interacting CMEs are significant and depend on the interaction region. As Prasad told that in his lecture, we need to understand which part of the CME is very crucial for producing the geomagnetic disturbance. So this study concludes that if there are many CMEs, then interaction region of the CME must be taken to predict its arrival, because it has some parameters which is very strong and produce very large geometric storms. Thank you.